After 7 decades of exploring our solar system, Aerojet Rocketdyne is now embarking on its next great space endeavor, sending humans back to the moon and creating a deep space gateway. This lunar outpost will provide explorers a safe place to live and work while preparing for the long haul to Mars. Our power and propulsion elements will play a central role in the orbital maneuvering and station keeping, life support, and other essential electrical components on the Deep Space Gateway. When the Space Launch System makes its climb into space, it will be powered by 4 RS-25 booster engines. Once the rocket has safely reached space, our jettison motor pulls the launch abort system away from the rocket. 4 RL-10 engines on the upper stage will then take over to propel the crew toward their destination. The Orion spacecraft's reaction control system, along with the European Service Module's OMS engine and auxiliary engines, will provide trajectory correction maneuvers. After 8 out of 8 successfully landed robotic missions on Mars and 5 orbiters circling the red planet, humans will soon be joining them. Sending habitats and cargo to Mars with electric propulsion ahead of the crew will enable shorter travel time and shorter setup time on planet. Additionally, we are working on nuclear thermal propulsion to quickly transport astronaut crews to deep space and safely back to Earth. The SLS rocket will also allow in-depth exploration of potential life-bearing worlds such as Europa. This extensive suite of propulsion will be responsible for opening this new chapter in space exploration, science, and discovery, and may one day reveal the answer to, are we alone in the universe? We're ready for the next giant leap in space exploration.
Hello, everyone. This is an entirely different angle than the one that I have when I'm hosting the podcast in the webcast in the aisle there. Thank you for joining us. We have some great panelists to talk about the InSight mission, the newest Martian that we Earthlings have put on or above the red planet is this lander. And in case you collect NASA acronyms, that stands for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. Quite a mouthful. InSight is the first probe designed to reveal the deep interior of Mars. And we'll be hearing much more about that and why we've sent it there and what we're already learning from InSight from our panelists. It arrived on November 26th last year, and I don't have the clicker. Can somebody advance this for me? I don't know if it's on the lectern, maybe. I should grab it. I think somebody had one. Yep, I see it. Sorry about that. So what you're looking at there is an intimate little landing party we had on that morning at Caltech's Beckman Auditorium. Intimate as in a full house of 1,200 people. And boy, did we all go nuts when we got the word that InSight was safe on the ground. The person that you're seeing there, second from the left, that's first my colleague Bruce Betts from the Planetary Society. Next to him is Troy Hudson of the Jet Propulsion Lab, who worked very closely with the DLR team on the HP3 instrument, also known as the MOLE, and we'll be talking about that as well. Then filling out the panel was Jennifer Jackson of Caltech. Here is a wonderful series of images. I think I'm hitting the right button. No, anyway, if you could go to the next slide. This is a great series of images taken by HiRISE on the Mars Reconnaissance Orbiter, our spy satellite at Mars. You are looking down at InSight, the lander on the surface of Mars, and if you look carefully, you can make out the parachute as well, which is pretty cool. Let's go ahead and meet the terrific panelists that I've been talking about. The first is an astronomer, an astrobiologist. Pascale Ehrenfreund has chaired the executive board of the German Aerospace Center, or DLR, since 2014. The DLR is the National Aeronautics and Space Research Center of the Federal Republic of Germany. She also serves on the faculty of George Washington University, not very far from where we are meeting today. Welcome, Pascale.
Just over the street,
Yeah, just almost across the street, yeah. David Murrow is the Deep Space Exploration Business Development Manager for Lockheed Martin, where InSight and so many other spacecraft have been built. He was on the Galileo and Cassini missions and Deep Impact even before coming to Lockheed Martin. I just mentioned MRO, which you guys also built. So you're looking down at another one that you're responsible for, along with the MAVEN mission, which has been tasting the atmosphere of Mars for the last couple of years. Welcome, Dave Murrow.
Thank you.
And finally, last but not least, Bob Fogel, or Robert Fogel, is the InSight program scientist at NASA headquarters. As you know, all NASA missions have a project scientist assigned to them at headquarters who is part of that team for that mission. Prior to arriving at NASA, he worked for the American Museum of Natural History, where he coordinated the science content for the Rose Center of the Hayden Planetarium, one of my favorite spots on Earth. He has been the program scientist for many other missions, including Phoenix, that great mission to the North Pole of Mars, or at least the Arctic, Grail, the Lunar Reconnaissance Orbiter, sort of MRO's sister circling the moon, which has given us so many of the great images we have of the lunar surface, and the upcoming Lunar HMAP CubeSat, which will be on the EM-1 mission, that first flight of the big rocket, the Space Launch System. Bobby, if you don't mind, I've got the first questions are for you, and we have some slides to go with them. And that is really just to ask you about the nature of InSight and its importance across all of these missions that we've been sending to Mars.
Thanks, Matt. Imagine for a moment that everything you knew about the human body was based upon just looking at the exterior of a person. You weren't allowed to probe inside the person. You couldn't take an X-ray. You couldn't take a biopsy. And you couldn't do an MRI or a CAT scan. Well, this would actually send us back not only many decades, many hundreds of years, but millennia, because we know that the ancient Egyptians did various different types of surgery, which is probing into the body. Well, this essentially is the state of Mars science right now. We've sent about 23 successful missions to Mars, orbiting Mars, flyby Mars, starting with Mariner 4, landing on Mars, and every single one of them had as its primary purpose was to look at the surface and to examine the surface. And so we know very, very little about the interior of Mars. Now, this is a little bit of an exaggeration. We have information from Mars meteorites. We have information from the two radars that are orbiting Mars, Charade and Marsis. But by and large, we've never sent a mission specifically to probe the interior of Mars. And that's what InSight has been sent to the surface to actually change. It is the first mission specifically designed to probe the interior of Mars, determine its layering, composition, and then to apply that information to tell us information about the other terrestrial type planets, Mercury, Venus, Earth, and even the Moon. Now, the InSight mission fits within the schema of exploration that NASA has held to ever since its earliest days, and that is flyby, orbiter, lander, and then rover. And that was established by Apollo. But interestingly, the first Apollo missions did not have a rover, so that's the lander. But one of the first things that they set up was a seismometer, which is to learn about the interior of the moon. When we first landed on Mars, we had a seismometer. It was strapped onto the Viking landers. However, it was not deployed on the surface. Now, what seismometers do is they measure vibrations. The best way that vibrations can be picked up is if the seismometer is actually on the surface. It was strapped on to the deck, a lander that actually had dampers in its landing legs. And so it wasn't surprising we didn't find any seismic activity on Mars. It was perhaps one event on Sol 80 that was recorded. But seismologists have been arguing about an actual event or not, for the last 30 years.
So we have a lot to learn.
Oh, yes.
Pascale, we're going to come back to you to hear about not the seismometer, but the other major instrument that's on InSight. We'll do that in a few minutes. But like virtually all planetary science missions nowadays, this is an international effort. And if you could talk about the DLR's participation in the mission.
Yeah, of course, it was a topic which was already discussed and also came in the questions the entire morning. So German space activities, they rely really heavily on international cooperation. And I think we are very proud that we have been part of NASA's exploration program for decades. We have contributed instruments to Sojourner, to Opportunity and Spirit. And right now we have contributed many different parts of the radiation assessment detector for the Curiosity mission. So, and now we are actually, the German Aerospace Center is very excited to be part of this mission, which is really unique. As Paul said, looking for the first time really in the interior. So I think in the framework of the European Space Agency, obviously there's a lot of collaboration, international cooperation, but also national cooperation. The German Aerospace Center has been building this instrument in Germany and was able to contribute to this mission. And that's, I think, makes us very exciting. And there are other partners on the InSight mission. And I think this is also a key to success.
Dave Murrow, with Lockheed Martin, you built it. Tell us about this spacecraft. And I know you have some slides to illustrate this.
Sure, I'd be happy to. So the spacecraft is great. There's my pictures. So the first picture on the top there is kind of a picture of the spacecraft. I think everybody's probably seen that on the web. We launched it just a little over a year ago on Cinco de Mayo in 2018. And then it just landed last year on Cyber Monday, actually. So you can see the spacecraft there. I guess before I get too much into the details, I do want to put a little bit of a plug in for some of the programmatics. The InSight mission, as you know, was built under NASA auspices with the thing that has been very successful inside the Science Mission Directorate that we at Lockheed Martin have participated in a lot is this discovery mission concept where missions are cost capped and they're led by a scientist. So I think Rob said it earlier when he was up here. To us, the science is really the most important thing. That's where we start. We ask ourselves, what are the questions that we need to answer? And then we build a spacecraft around that. Turns out, when you land on Mars, unless you have a rover, there's a design that we've done for a while. And so back in the 70s, Heritage Company, Martin Marietta, built the 2 Viking landers. And then we built Phoenix, which launched in 2007. And it's very similar to what you're looking at on the screen here, which is InSight. So I guess one of the things I want to say is that practice certainly helps. Being able to do the same kind of design and the same kind of mission a number of times both brings down the cost, brings down the risk, and lets you do things that you might not have been able to do on the first mission. We heard a little bit about the early seismometers. Didn't quite have the results that we wanted. So you can see there in the just below the left-hand solar panel there, you can see the seismometer with the windshield over it. We learned, and we've done better. So the InSight spacecraft there that you can see the robotic arm sitting on top of the deck. That's what deployed the seismometer and the windshield separately, and it deployed the HP cubed, affectionately known as the mole, over there on the right-hand side, which is the instrument there that's there on the front of the lander there on the ground. So the 3-legged design has served us very well. We're very proud of it. You can see there on the left-hand side in the bottom, just some of the steps we go through to make the spacecraft work. We obviously have to test it. That's acoustic testing that I'm showing there. It's all buttoned up. The entire spacecraft is right there in that capsule. And the piece you see at the bottom there with the flat panels, that's what we call the cruise stage. It actually powers and controls the spacecraft on the way to Mars, and then it gets deployed just before the quote-unquote 7 minutes of terror begins. A little bit more on that in a second. So then there's the spacecraft. You can see a top view of the spacecraft with some of the technicians all deployed, getting tested in our high bay. Oh, not quite ready for that one yet. And then there's some parachute testing and a leg deployment test there on the bottom right. So a lot of things, and like you said, it went very well. As a matter of fact, during cruise, we had a little bit of a hiccup during cruise. There was a thermostat that wanted to dither, go back and forth, turn the heater on and off on one of the thruster lines. Not really a problem usually. We had the command all ready to send up, and it was fixed. Actually, the engineer says that it was fixed almost in record time. So cruise went very, very well. And then came the 7 minutes of terror, where we enter, the spacecraft comes apart, the heat shield pops off, the parachute comes out back, as you can see, to slow the thing down. We finally come down, and you can see on the next picture, this is actually what happens when the spacecraft lands. So I know you've all seen pictures of various different places where folks were. This is at our mission support area in Denver, where we command and control the spacecraft. We send all of the commands and the sequences to the spacecraft. We actually build the commands for all of the spacecraft subsystems and bring in all of the science payload sequences from our various partners.
Yep, that shirt looks familiar, Bobby.
Oh, yeah.
And that shirt looks familiar. Yeah, we didn't coordinate, honestly. So, but you can see our team there, and Pete there in the bottom or in the top left picture. Thumbs up for the successful EDL. So that was a great day for us there in Denver. The second one recently, of course, Phoenix that you mentioned was another successful EDL. So then moving on, we've actually been on the surface now for a little over 100 days. So if we go to the next slide, say just a little bit about what it's like on the surface. So there at the top left is a selfie that we took, and those selfies actually are kind of complicated. The robotic arm has to move around with the camera on the end and take a lot of different pictures, and then they get all stitched together on the ground to turn into a selfie. So we did that on Sol 10, and you can see on the other side, we did that also on Sol 106. That was actually about a year from launch, even though it's only 100 days on the surface. So 96 days, as you can see from those two pictures, really makes a difference. The environment on Mars is dusty. No surprise there. But one of the very interesting things that we had, and this kind of tells you a little bit about the importance of talking across programs, during the course of the cruise to Mars, we discovered, actually the JPL scientists discovered that looking back at all of the dust environment over history, looking back at what's happened in the 70s, looking back at what happened with some of the Odyssey measurements, looking back at what happened with Opportunity. Opportunity went dark because, well, the opacity of the environment, the opacity dust of the atmosphere got very, very dark. And you can see that here. This is actually not that bad, not nearly as bad as what was compared with Opportunity. But we had to sort of scramble during the cruise phase and design the mission to make sure that even with the maximum opacity, which is a tau of 11, they honestly said, let's turn this up to 11. Thank you. With a tau of 11, we had to be able to design the mission to be able to do all of its nominal surface operations, even in that state. We were able to do that. Luckily, it hasn't been nearly that dusty or nearly that dark. You can see a fair amount of accumulation, but everything has gone really quite well for us. We deployed the seismometer with its sun shield. We deployed the HP cube with the mole. We began some hammering, and I'll let Pascale talk about the status of that. And we're learning a lot, and I'll let Bobby talk about the seismic events that we've had. So very proud to be part of the spacecraft. Look forward to more of these in the future with your help.
You bet. You can sure see the legacy of Phoenix, but I heard that one of the differences between Phoenix and InSight are the larger panels, partly to compensate for what was expected, the dust.
Yes, the larger panels are one of the pieces. Those panels can be expanded and retracted or made smaller. Those are the same panels that are flown to the International Space Station nowadays. So,
are you still hoping for a dust devil or two to sweep those off?
Well, we would like to see that, yeah, and maybe we'll somehow vibrate them a little bit to make them shake off.
You've heard a little bit about the two major instruments that InSight has brought to Mars. Bobby, tell us more about the seismometer and a change that happened literally since we first talked, just in the last few days. It's doing its job.
Right, so let's start with this. This is one of the most complex seismometers ever built. There are more sensitive seismometers that are deployed on the Earth, but we're deploying this on Mars.
It's exquisitely sensitive.
Right, it's so sensitive that it can measure deflections the size of a hydrogen atom. So that's 1 angstrom, or 10 to the minus 10 meters. And for those of you who don't play in engineering terms or science terms, that's a decimal point with 9 zeros and then a 1, meters. And when you're deploying that on a planetary surface 200 million miles away, it has to be done with absolute care and delicacy. We started our deployment in December, and where the arm put the actual instrument onto the surface of Mars. And then we had to actually bring down the tether so that it's sitting flat on the surface, which goes directly to the seismometer. And then we had to place a wind and thermal shield on top of the seismometer, because as all seismologists know, seismometers love to pick up things, and they pick up vibrations of movements of weather and a spacecraft even better than it does Mars quakes. And so our wind and thermal shield protects it from the wind, from Mars winds, and from temperature deflections. Now, we turned the seismometer on first on the deck for small amounts of time, and we had lots of noise, which is what would be expected, because as the sun beats down on the spacecraft actually creaks. It's not anything that we would hear, but a seismometer as sensitive as SEIS, which is the name of the seismometer that we've deployed, can hear that. But after we put it down and placed our wind and thermal shield on it, we have unprecedented accuracy. Our noise levels are better than spec and better than we had in the laboratory, and we're all very delighted with that. Now, it turns out that Mars indeed is, so far, extremely quiet. That being said, we've already had 6 events, of which Matt just mentioned one of the events was reported just the other day. Of those 6 events, I call those seismic events. Those are events that happen based upon the geology of Mars, not based upon wind, not based upon the spacecraft. Seismic events. Of those, 1 event is a very likely candidate for a Mars quake. Now, what we're looking for is a large Mars quake, probably of the order of magnitude 4 and above. We hope to get a whole bunch of those.
Same kind of magnitude Richter scale that we deal with here.
Richter scale, exactly. The quake that we had was much below that, which was something on the order of magnitude 2.5. If you're not familiar with the Richter scale, it's a logarithmic scale. So a quake magnitude 4 is 10 times as powerful, releases 10 times as much energy as that of a quake that's 3. This one, which occurred on Sol 128, was about a magnitude 2.5. From this information, we've gleaned that the epicenter is probably about 150 kilometers away from the InSight landing spot. Now, normally a quake, when you see it on a seismometer, doesn't take very long, because quakes last 30 seconds, 10 seconds, 5 seconds. A huge quake will last minutes. But this was a very small. However, the wave train, that is the amount of waves that we get for this, lasted for about 12 minutes. So what do we learn from this? Well, that pattern is seen by Apollo on the surface of the moon with the Apollo seismic networks that was placed down by the astronauts. And what we've learned from that is, turns out that the moon was very shattered by impacts. And so there are large blocks and pieces of the moon that are all put together and shattered, both the regolith and the subsurface. This shattering causes scattering of seismic waves. So if this is your epicenter and this is your seismogram, normally on the Earth it goes directly there because the Earth isn't shattered the way the Moon and Mars is. But if the crust of Mars is shattered or the Moon is shattered, then as the wave travels, it hits different reflectors and it moves around, and it does not take a straight path to the seismogram. And so that elongates the wave train, and that tells us exactly what's going on in the crust between the InSight lander and the epicenter of this seismic event. What do we learn from this? Well, one of the things that we learned from this is that in the crust between this epicenter and the InSight lander, there probably isn't that much water, because one of the reasons why we don't get this sort of scattering in the Earth is because we've got water in the crust, and that water has a tendency to heal the minerals that have been shattered. And so at least for this small area of crust that we've determined so far, there probably isn't that much water, and it's not likely that there was much water all the way back to Hesperian age, which is pre-3 billion years ago.
Wow. So it's doing its job. It is revealing the interior of Mars. 6 events, only one of them so far probably a Mars quake. Right. Is that more or fewer than were expected?
So far, that's actually a lot fewer than we're expecting. Now, we don't necessarily expect all the events to come together on the moon. There are cluster events of seismic activity. Perhaps that's what's going on Mars. Our scientists are doing lots of calculations right now to determine how many we should expect in the upcoming 2 years, year and a half. But we're all hoping for a large event, which is what we need in order for us to help determine exactly how Mars is stratified: core, mantle, and crust. We need a large event that would have to be greater than magnitude 4, where we can actually see the different types of waves, P waves, S waves, surface waves. That would help give us the wonderful information that we're looking forward to in order to interpret the interior of Mars.
And I bet you're wishing that Dave and his colleagues could build 2 more and put them other places so that you could kind of triangulate.
Right. Well, that would certainly be
we'd be very happy to do that job.
Okay. We'll talk to the administration.
The triangulation would be, of course, ideal, which is exactly what we do here on the Earth. We have thousands of seismometers, and we use all the seismometers together in a network in order to tell us specific information about not only what the epicenters are, but how the Earth is stratified. We know a lot about how the Earth is stratified. However, for InSight, it's sort of like a time machine. We're going back in time. The first seismometer that successfully picked up a quake on the Earth did so in 1889. And this is the 130th anniversary of that.
Wow.
And so that is paralleling what we're doing on InSight on Mars. And those early seismometers, where they only had one station, had to use very creative methods in order to tell us how the Earth was stratified. And we're using some of those very methods in order to be able to determine the interior of Mars based upon one seismic station.
I want to get to yet another bit of experimentation that InSight is doing, even though it doesn't really have an instrument for this, which we'll address briefly. But there is one other charming fact about the SEIS instrument, or really rather the shield that goes over it, which is a tie to, if anyone has ever been to a Renaissance fair or a Society for Creative Anachronism, do you know what I'm getting at? Chainmail. Could you just, why chainmail? Actually made by a company that makes chainmail for people who go to the Renaissance fair.
Right. I have to say, I don't really know exactly why we picked chainmail for that, But the chainmail is weighted. And the chainmail, the skirt that you're talking about on the windshield actually has to go down. And after we placed it on and we opened up the hoops that hold the chainmail, it slowly, over a period of time, actually went all the way down to the surface. So we were really happy with how that performed. I do have one chart to show.
Yeah, we should do that next, because this is actually a video, and it has audio. Hopefully we can play this back. But this is that Marsquake that
This
you were
is the
telling us
Marsquake.
about.
We released this about 2 or 3 weeks ago. So you might have seen this in the news. But before we hear the audio, just let's take a look quickly at what the trace looks like. The upper and the first and third panels that you have there are basically the same information as you do in the second and third, which is probably what you're normally thinking about when you think of a seismogram, except the first and the third are actually the seismic profile for various different frequencies. So let's just ignore that for a moment. If you take a look at the different panels, you'll see that first we're going to hear what the Mars wind sounds like. And this is early morning of Sol 128, where there was some wind blowing. And then we have the Mars quake. And then the robotic arm was moved. It was pre-programmed to move later on. And so what we've done here is, as you know, a seismogram is just a plot of vibrations that a seismograph has felt from the surface. We can take those same vibrations and just move them up into frequency that's audible so that you can hear what this sounds like. So let's listen carefully as we first hear the wind, then the Mars quake, and then the robotic arm move.
And you'll see this track across each of those.
Awesome.
It's great. It's appropriately eerie.
Right. Now we're hoping to be able to come back and play the same thing for you with a magnitude 5 or 6, where the robotic arm sound is not higher than the Mars quake.
And we'll do it next time. Maybe by next year, we'll have Sense-Around attached to your seats so that you'll have the shaking of the seats as well. Very briefly, about this other experiment called RISE.
Oh, RISE is a phenomenal experiment. It's the closest thing to magic that we'll ever do. What we do is we use InSight's communication system, the X-band communication system that we sometimes speak to InSight directly from Earth with, and we're using knowledge of the speed of light to determine how Mars has turned or rotated over a period of time. So what we do is we send a signal from the Earth, and it hits the InSight lander, and it spins it around, and it sends a message back to the Earth. And in that time, between sending the message and receiving it, Mars has turned a bit, okay? And so we're learning about how Mars is turned, but this is so precise that we know the distance to InSight within about 1.5 feet from the Earth. And by listening in over and over, doing this a half hour a day, every single sol, we'll be able to determine exactly how the spin axis of Mars precesses, that is, rotates over time. And it's so sensitive that we actually determine what's called the nutation, which is the precession of the precession. It's another level of that. And once we have this information, we will be able to determine what Mars core is like, how big Mars core is, and perhaps whether there's any liquid in the Martian core, which is one of the big unknowns for Martian science. And that will dovetail with information that we'll be getting from the seismometer.
Fascinating. Pascale, you've waited patiently to tell us about another instrument, the other instrument that InSight carries, which has generated enormous excitement and more recently concern. Tell us about HP3.
Yeah, I have actually a few slides. Maybe they can be shown. And it's very nice to be patient here because the pillows are just awesome. Yeah, here, whoever sits on the panel this afternoon. Yeah. So this is the HP3, also called Heat Flow and Physical Properties package, which consists of a mole and a theta. And of course, it tries to explore the Mars core, mantle, and crust. It is actually trying to dig down, a hammer down, it's not a drill, for 5 meters. So right now we are in 30 centimeter, but I will come back to that. But I think we are quite proud, and you see here in the video the hammering mechanisms. It's a very complicated technique which we work together with Polish industry, the Academy of Sciences and Research Institutes, and it's an electric motor which has a rotating element bringing tension to a spring which has the hammer attached, and it actually takes a theta down with sensors in order to measure the heat flow inside of Mars, and also looks at the temperature increase, of course, when it goes deeper, and that gives you indication. We talked a little bit about that, what materials are actually producing the heat and how can we actually compare that to Earth. So we are, I think, very excited to be part of that. And when I look at the next slide, we are since the 12th of February on the surface. And there have been several hammering sessions which were activated. I think activated by the 1st of March was the first hammering session. And it goes a little bit slower than we imagined. And it's always difficult to see what you actually imagine. Right now, we are approximately in 30 centimeters, and the analysis is imaging, seismic. I will come back to that. And we also take thermal data and radiation data, because we have also a radiometer, which measures in the infrared, which is more or less equivalent to the surface temperature on Mars, which is also measuring on the surface. And because we are a little bit stuck at 30 centimeters, we had to find out what's actually the reason. And there are many different techniques, and it's a real teamwork to find out how we go. Because the size instrument, which was just explained, is trying to measure the hammering and in particular the interval between the hammering strokes, and the camera of the robotic arm is actually looking if everything goes well and the theta is actually descending with the instrument. We have also, of course, a spare instrument where we are doing tests with different soils and regoliths in JPL, actually, and also in Bremen in Germany, in order to simulate. So it's really so Apollo 13 style, yeah, to see how we actually can go further before we continue. So we had this diagnostic hammering in March, and actually just a few days ago, and I don't have all the results yet. They have to be evaluated. But when you look at the size instrument, is actually measuring this interval of the hammering strokes, and you can actually see that if you would be really nicely hammering, you would be on an interval of about 100 milliseconds. And if you are going against a gravel, a rock, you would actually have a rebound, and then you would actually drop to 50 milliseconds. And diagnostic hammering, the size instrument measured that we are about at nearly 80 milliseconds. And that means we are somewhere in between. So this is the way how you find out. So it seems not to be rocks, though we have actually already moved one rock away, I think in the first 10 or 20 centimeters. The instrument is able to do that. There was an idea that, there could be some kind of that the instrument could be tied up, in the support structure, but it looks like that it's actually the hull friction is limited, and we have to make more tests in order to see how we can hammer further, because we want to go to as deep as we can. The more data we have and the more measurements we have, we will have great ideas about, and also, of course, with the other instrument, about the interior of Mars. And I think I have a final slide. So all the tests have shown that HP3 is really healthy and operative. We just have to optimize to hammer further down. And the radiometer, which is on the surface, and gives really excellent results. So the daily Mars surface temperature has been measured between 185 and 285 K, and there have been some eclipses through Phobos, by the sun, and these are about 30-second events, and you can actually see that the temperature drops 1 degree. So this is quite interesting. And generally, instrument is extremely sensitive, 0.5% of accuracy, and we are just all working together now in order to go further down into the surface.
So we're far from giving up on this.
Oh, absolutely, yes.
And just what has been attempted so far? I mean, in a sense, it has proven the technology.
Yes.
It's a shame that that rock got in the way. Hopefully you'll work around it or through it. But it really is unprecedented, the depth to which we still hope HP3, the mole, will reach on Mars.
Planetary science is exciting. The DLR also landed with Japanese space agency JAXA on the asteroid Ryugu, and this was also a very exciting event, because you never know what actually happens. You don't know exactly the material you are facing when you go to a planetary body. So I think this brings us all very close together and working together in order to solve all these issues. And it's exciting.
So, gentlemen, we have to leave the stage, and so we won't have time, I'm afraid, for audience Q&A. But all of our panelists will be here. You can catch them if you have specific questions about InSight. But I wonder if either of you have any last comments about the status of the mission as well, going as healthily as apparently HP3 is.
So I'll say that the spacecraft is doing great. We're flying 8 of them right now in our mission support area, and this is one of the easiest ones because it's on the surface. So we look forward to as many more diagnostics as we need, and finally getting data back from down deep in the surface.
Yeah, the spacecraft is healthy. The seismometer is doing fine. The other instruments are doing really well. HP3 has had a little snag, but we're deploying lots of person power to it to try to solve this problem, both at DLR and at JPL. And we're very hopeful that we'll be able to push forward.
You bet. Thank you so much, all three of you. Best of luck as the mission continues. Please help me thank our panelists.